All right, this is your related rates review for your test. In question 1, we have the oil spilling from a ruptured tanker spreads in a circle on the surface of the ocean. The area of the spill increases at a rate of 9 pi meters squared per minute. How fast is the radius of the spill increasing when the radius is 10 meters? So let's see. Notice that I've given you the formula, and I will give you the formula on the test. Your equation, the area of a circle. So let's see. If we do the derivative of this with respect to time, we have dA over dt equals 2 pi r dr dt. And now let's see what information we were given. The area of the spill increases at a rate, so the area of the spill increases, so that's dA dt. So I know dA dt is going to be 9 pi, and we have meters squared per minute. And let's see, how fast is the radius increasing? So that's dr dt, because that would be a change in the radius. When the radius is, so the radius is equal to, and that's a r, is equal to 10 meters. So it looks like we have everything we need to go and plug in. So I'm going to rewrite that so it'll look a little bit better. There we go. So let's come over here and start plugging into our formula. And so let's see, we have dA dt is 9 pi. And we do have meters squared per minute. So you're welcome to put in those units. Squared per minute equals 2 pi times our radius, which is 10 meters. And rate of change of our radius is what we're looking for, dr dt. And so let's see, when we divide all of this over, it looks like we have 9 pi meters squared per minute over, and again, don't worry about multiplying all this out. I would just wait about doing all of that, because you end up canceling a lot of this out. So notice that the pi's will cancel, and let's see, one of these meters will cancel. So it looks like dr dt, or the rate of change of the radius, is going to be 9 over 20. And let's see, meters per minute. So, and that looks like that would make a little bit of sense. All right. So there's going to be our first one. So you need to expect some problem like this where you have to find the derivative of a given formula and do some straight plugging in. All right. A lot is on the ground 20 meters from a building. So we have a lot on the ground. So let's draw us a building. And 20 meters from that is going to be a lot that is on the ground. So there's 20 meters. And that is 0 there. And a man 2 meters tall walks from the light directly toward the building. So we have this nice stick figure here. And he is walking toward the building at a rate of 1 meter per second. So that's going to be some kind of dx dt. And that's going to be 1 meter per second. And so how fast is the length of his shadow on the building changing when he is 14 meters from the building. So this light we're going to assume shines up this way. And so I want to know how much is his shadow changing here. So since we're looking at this direction, I can assign this side. Now we don't know how long his shadow is. We don't know how long the side of the building is. We're going to call that y, and then we're going to talk about dy dt being what we're going to be looking for, in which that's the rate of change of his shadow. Now, let's go back and label a few other things we know. We do know that when he is 14 meters from the building, we want to know what is the rate of change of his shadow. Now, of course, we know this value over here would be 6, but we also need an x value in here, something that we can take the derivative of. Because remember, with related rates, we need some kind of formula, something with x and y, so that we can do the derivative. So really, we have some kind of similar triangle set up here. We know this guy's height is, what, 2 meters. So let's see. We could set up some kind of proportion here. We've got a small triangle here that we could look at. And then we also have this big triangle up here that we could look at. So we have similar triangles. So let's see again. We've got here, we know this side length here is 2. We know this entire side length is 20. We've labeled this side to be x. We've labeled this side to be y. So it looks like we can say, well, this base here of this small triangle, x, to the base of the big triangle over here, which is 20, is equal to, and let's see, we would say this side of the small triangle over the side of the big triangle, y. And now we have our x and y that we can work with. To solve this proportion, let's cross multiply. So I would have xy equals 40. Now we've still not done a derivative yet, and notice it's x times y, so we're going to have to do our product rule. So we have first times the derivative of the second plus the second times the derivative of the first equals, and if we take the derivative of 40, we're going to get 0 because it's a constant. Now we can plug in that value that we know for x. That's that 6 that everybody always wants to grab. So let's go ahead and start plugging in what we do know. So let's see. Our x value, I'm going to move this up here. Our x value is 6 times dy dt. Well, that's going to be the length of that shadow, how it's changing, plus, and then y value. Well, what's going to be our y value? So let's see, what would be that y? Well, I don't know. I don't think I know a y value just yet, do we? So, God, we're going to have to come back down here and look at this. We know this relationship, don't we? We know x times y is 40, and we know x is 6, so y is going to have to be 40 over 6, isn't it? So we have 40 over 6 times, and then our rate of change of x is going to be 1. And let's see, all of that's going to have to be equal to 0. And so, let's see, we have 6 dy dt is equal to, and let's subtract over 40 over 6 and reduce it, so that's going to be negative 20 over 3 dy dt equals, and we have negative 20 over 3 times, and I'm going to multiply both sides by 1/6. So it looks like our dy over dt is going to be see negative 20 over 18, which is going to be either you can leave that or negative 10 over 9. And let's see, what would be the rate of change there? It would be meters per second. So there's our rate of change. And does it make sense that that's a negative rate of change? Well, he's walking away from the light, so would his shadow be shrinking or would it be growing? I think we should have a negative rate of change. I think it's probably going to be shrinking. In the right triangle shown at the right, the angle theta is increasing at a constant rate. So notice we've got an angle increasing constant rate 2 radians per hour. So that's going to be d theta dt. It's increasing at a rate of 2 radians per hour. And let's see, at what rate is the side length of x increasing? So we're looking for a dx dt. When x is 4 feet. So we also know that's 4. So hopefully we see that's probably going to be a 3. And gosh, so we need to find this x, the rate of change of that x, but we're given a rate of change of an angle. Now, we want to jump on the x squared plus y squared equals c squared train, but that's not going to help us when our rate of change of the angle is given to us. So let's think about what we're given. Well, we know we're given a rate of change for theta. This side is x, so that side is opposite. And this side over here is our hypotenuse, and we're told that that is 5. So looks like we need to incorporate the trig function sine. And so we're going to say sine of theta equals x over 5. Or you can think of that as 1/5 x. So that's how I would think of it. Make it a little bit easier. Now we need to do the derivative. Remember, you set up some kind of formula and then you do the derivative. So the derivative of sine of theta is cosine of theta times the derivative of your angle. So that's where we're going to incorporate d theta dt equals, and if you think about this up here as 1/5 x, then the derivative of 1/5 x is just 1/5 dx dt. And dx dt, oh my goodness, I wrote dx, goodness help us, dx dt. So now let's talk about, well, what is cosine of theta? Well, that's where we're going to use that 3. And cosine of theta is going to be 3/5 times d theta dt equals 1/5. Oh, wait, we know d theta dt, don't we? Oh my goodness. So let's go back. What do we know about d theta dt? D theta dt is 2, isn't it? 2 radians per hour equals 1/5 dx dt. And so now it looks like all we need to do is multiply both sides by 5. And so we have 5 times 3/5 times 2 equals dx dt. And of course our 5's are going to cancel. So we have 6 equals dx dt. And our units, which we do need to include, would be radians per hour. Right, so number 4, gravel is being dumped from a conveyor belt at a rate of, and notice that's cubic feet per minute. So that's going to be, looking at our formula, which is a volume, So we're going to have dv dt is going to be equal to 30 feet cubed per minute. And its coarseness is such that the pile forms the shape of a cone whose base diameter and height are always equal. Oh, well, that's handy. So I know my diameter is equal to the height. So let's see, the diameter is 2 times the radius, isn't it? 2r equals our height. So we have that relationship, and I go to that relationship because our formula has r and h. How fast is the height of the pile increasing? So we need dh dt. So how fast is the height of the pile increasing when the pile is 10 feet high? So we know h is 10. Okay, so let's go through here. And if we're looking for dh dt, then we need to ensure that we keep an h in my formula. So notice that I know that r is 1/2 h. So I'm going to make that substitution over here so I don't have the product rule. So whenever I come over here in my equation, before I do the derivative, I have 1/3 times, and pi, oops, I'm going to put pi up here. I'm just running out of room. So 1/3 pi, or pi over 3, 1/2 h squared times h. So we can clean that up a bit. Let's see, so that's really going to be pi over 12 and then h cubed. Well, that's a little bit easier to do the derivative. We're going to say dv dt equals, and if I move that 3 down, that 3 is going to cancel with the 12, so I have pi over 4 and then h squared dh dt. And dh dt is what we're looking for. So let's go plug in values that we now know. We know the volume is going to be 30, and I'll come back and attach units at the end. Pi over 4, h, well, what do we know about h? What value were we given? It was 10, so I have 10 squared. And then we're looking for dh dt. And so here we're going to get 100, aren't we? 10 squared is 100, 4 cancels, and that 25. So all of that is going to leave me 25 pi. So dh dt is going to be equal to 30 over 25 pi. And we can reduce that or leave it like it is. And so how fast would that be changing? Well, let's look at our units. It would be feet per minute. Okay, moving on. All right, our last problem, and it was an old free response question. The very first part, they've given us a good bit of information here. Let's see. The figure below represents an observer at point A watching balloon B as it rises from point C. The balloon is rising at a constant rate of 3 meters per second. So that 3 meters per second, that's the balloon rising. So I think that would be a dy dt. It's going to be 3 meters per second. And let's see. And the observer is 100 meters from point C. So we have 100 here. Find the rate of change in x at the instant y is 50. So when y is 50, oh goodness, so let's see. We're going to have to go through the Pythagorean Theorem here. and come up with that x value over there, I do believe. So let's see, find the rate of change in x the instant that y is 50. So we're looking for dx dt. All right, so let's go through, and I would go ahead and find that missing side here. That's going to be a right angle. And so be careful in assuming we don't know what that hypotenuse is. We know x squared is going to be equal to 100 squared plus 50 squared. So x is going to be equal to the square root of 100 squared plus 50 squared. And so I'm going to say that ends up being 50 root 2. Sorry, not 50 root 2, it's 50 root 5. But double check that in the calculators, but I think that's right. So we know that x value, and gosh, what else do we know? Well, we know this side squared plus this side squared equals that side squared. So I don't know what to call this side. We'll call it z. That looks like a 2, but I'm going to pretend it's a z. So we know z squared plus y squared equals x squared. And this is completely backwards from what we're used to. Now when we start doing the derivative though, hey, this value right here though, it's the length that that person is standing away from point C. That's not changing. It says the observer is 100 meters from point C. So he ain't running anywhere, so he's not going to have a rate of change. So when I do the derivative, that's all going to go out to 0. Hallelujah. All right, so then that's going to give me to y dy dt equals to x dx dt. And of course, I'm going to say bye-bye to all those 2's. And we know y is 50. Hey, I'm feeling this problem is coming together. 50 times, we know dy dt, 3 equals, again, I dropped those 2's, x, which we just saw for, which is 50 root 5. What in the world? And then times our rate of change, dx dt, which is, hey, what we're looking for. So when we divide everything over, we have dx dt equal to 50. Notice I'm not multiplying a thing out, and I encourage y'all not to. Not until the very end. And notice, oh, my gracious, that's a 5. That 5 is really being stubborn. 50 root 5. And so here we can cancel out those 50s, yippee. So dx dt is, drumroll, 3 over root 5. All right, let's see what else is in store for us with this problem. Okay, so, oh wow, now we've got to find the rate of change in, I'm pretty sure that's not ion, in the area of the triangle the instant when y is 50. Oh, okay. Well, let's see. The area of a triangle is 1/2 base times height. And so, let's see, dA over dt equals, and I would just leave 1/2 sitting out here to the side, just discriminate it a minute. So we have first times the derivative of the second, so dh over dt, and then plus the second times the derivative of the first, db dt. All right, okay. So at the instant when y is 50, well, we already have some of this information already. So let's go back and look. We have the base times the rate of change of the height, plus the height times the rate of change of the base, and the base isn't changing. So this shouldn't be too bad to start plugging in. Let's see. dA dt. So get this pen going. dA dt is equal to, and of course just bring down our 1/2, our base, which is 100, times the rate of change of the height. And what was that rate of change of the height? The rate of change was 3, so that was given to us. So that's going to be 3 plus the height, which is 50, times the rate of change of the base, which is 0. The rate of change of the base is staying stationary. So let's see, what is all that going to give us? We end up with 100 times, or 1/2 times 300. And you can leave it like that or write 150. Okay, so there's the dA dt. Now we need the rate of change of the angle, the instant. Oh, gracious, this is the never-ending problem. So let's go back. Right here's our angle that it would be talking about, the rate of change of that angle. And let's see, we need to use at least one of our given. So I would do opposite over adjacent. So we're going to have to do tangent. So I would do tangent of theta equals y over 100, or 1 over 100y. And now we need to do the derivative. And the derivative of tangent of theta is secant squared of theta times d theta dt. And that's what we're going to be looking for now, is the rate of change of theta, equals, and again, think about this as 1 over 100 y, so the derivative there is just going to be 1 over 100 dy dt. And we know the rate of change of that side. That's what we were given at the beginning. So, well, we need to know secant of that angle. And secant's the reciprocal of cosine. So if cosine is adjacent over hypotenuse, which would be 100 over that 50 root 5, well then the reciprocal of that, so that's going to be 50 root 5 over 100, and that's all squared d theta dt equals 1 over 100, and the rate of change of y that was given to us earlier is going to be 3. And so let's see, I'm not real eager on multiplying all that out. I would leave it. This is a free response question and you would get full credit for it. If it was not a free response question, then this would be a calculator problem. So don't be concerned about all these numbers. We have 3 times 1 over 100, or 3 over 100. And then if we divide all of that, then it's going to be 100 over 50 root 5, all squared. And you leave it just like that. As far as units for this, it's the rate of change of the angle. So this would be radians per, I would think, seconds. I think that's what the time value was. Okay, I hope this helps, and I hope it gets y'all ready for your test coming up on the blog day.